All right, today's notes are going to be on the immune response, and specifically today, the innate immune response. So before your body really kicks into gear all of the specialized immune responses that we have, this is just what's going to happen anytime you get a particular infection. So here's your skin. And your skin is filled, obviously, with skin cells, but there's also these little mast cells that line your skin. And their job is to sort of signal whenever there is a problem. Namely, the problem would be if you step on a rusty nail or, get a splinter or something like that, and that initial barrier is broken. Because remember, our innate immune system's real bread and butter are all of the physical, chemical, and biological barriers that we normally have. Like skin is a physical barrier. The bacteria that lives on your skin is a biological barrier. The acid that is in your stomach is a chemical barrier. The mucus that lines your nose and mouth and any opening to the outside world is a physical and chemical barrier. It kind of traps pathogens and can kill them. But today we're going to talk about what happens when those barriers get broken through. So, a little bacteria makes its way into your body from that rusty nail. The first thing that happens is that neutrophils are released. Neutrophils are actually floating all through your blood and lymph at all times, and so they get there quickly. And neutrophils' job are to digest bacteria, but then they die. Neutrophils are not particularly great fighters. They're sort of like a 1-to-1 ratio. When they kill something, they also die themselves. You've seen a lot of dead neutrophils before. Anytime you have pus from a wound, those are dead neutrophils. Oftentimes acne, like whiteheads, that's all dead neutrophils that are building up under a surface layer of your skin. They're fighting some bacterial infection, and when they die, they make pus. The next guys up are macrophage. Macrophage means big, phage means eat. These guys are big eaters. They can kill many bacteria at one time. They eat the bacteria and then they present the bacterial antigens on their surface. We'll talk more about these guys when we get into the adaptive immune response, but these guys are basically, you can think of them in terms of Mad Max and Thunderdome, where you wear the disembodied remains of your enemies on your surface. That's what these macrophage do. They'll eat a bacteria, and then they'll break it down and digest it, and then they'll present its antigens on the surface of the of the macrophage in order to teach your adaptive immune cells what to target. So they're pretty cool. But by far the coolest cells are the natural killer cells. You could call them NK cells, but I see no reason to call them NK cells because natural killer cells is just too cool of a name. So natural killer cells patrol blood and lymph looking for infected body cells. And when they find an infected body cell, they destroy it. Natural killer cells are some of the few cells in your body that have been given the okay to kill your actual body cells. So they're not trying to kill bacteria, they're trying to kill your body cells. Typically, your cells get infected with a virus or cancer, and that is when natural killer cells step in. So here's a happy little cell in your body. It's presenting a particular antigen, like we learned about A antigens and B antigens. This little guy is presenting the same antigen that every cell in your body presents, MHC class 1. It lets you know, hey, it's cool, I'm supposed to be here, and your immune system doesn't bother it. It stands for Major Histocompatibility Complex 1. So it just means that it's a cell and it's compatible with your body. Major Histocompatibility Complex 1. These cells, unfortunately, have been infected. It either has a mutated MHC class 1 or a missing MHC class 1. And when a natural killer cell comes in contact with a mutated or missing MHC class 1 cell, it's got one job to do. It kills those cells, right? It pokes them with a little protein, an enzyme that eats away their cell wall. And so natural killer cells kill your own cells by poking them. And it triggers something called apoptosis, which is, just like it sounds, it's popping that cell. Technically, it's called programmed cell death, but really it's just popping that cell. Okay, so that's like the initial onslaught. That's before your body even realizes something is wrong on a like systemic level. These are the first responders. The secondary response is inflammation. Inflammation includes redness. The redness is a function of vasodilation, bringing blood vessels closer to the surface of your cell so that you can get more macrophage and neutrophils there. Swelling, again, that same vasodilation brings more proteins to that particular area so that the proteins can start to fill in whatever cut was made there and start to form a scab. So that would be like fibrinogen that turns into fibrin, as well as platelets in your blood would clot that area and form a scab. Heat, that area heats up because the warmer your body is, the faster your cells metabolize, which means they eat more and divide more quickly, and you want your cells dividing more quickly because that will make more macrophage and natural killer cells and neutrophils. And then pain. That's basically your body telling you, hey, whatever you just did, don't do that thing again, right? Like that rusty nail, avoid it next time. So pain is a way of you not continuing to injure yourself. Then we get these little mast cells, these blue cells that are lining your surface, and they have a very particular job. They release histamines. You've probably heard of an antihistamine like Benadryl or Claritin. Histamines are proteins that trigger inflammation. You take an antihistamine for allergies because your body is overreacting when you have an allergy. That pollen is not going to kill you. You are perfectly safe from the pollen. But your body doesn't know that, and so it triggers an immune response when you come in contact with pollen. Same thing with people with peanut allergies. That peanut oil is actually not going to hurt you at all. What hurts you is your body's response to the peanut oil. That is why you have to carry an epinephrine pin. Epinephrine is really just adrenaline, and adrenaline stops this inflammation and immune response. So mast cells trigger inflammation through vasodilation. Vasodilation results in all of that inflammation. It makes blood vessels large. So here we see all of these mast cells releasing these histamines. See those little blue histamines up there? And so what it does is it takes your normal sized blood vessel and it increases the diameter of that blood vessel, which actually makes the blood vessel walls thinner, and it's easier for macrophage and natural killer cells and neutrophils to sneak through. So there we have some macrophage sneaking through. At the same time as histamines are being released, cytokines, cyto means cell, kine means movement, so these proteins get cells moving. They're being released to attract more macrophage, neutrophils, natural killer cells, dendritic cells to the infected area. So here we have these little green guys being released. Those are cytokines. And now we have, after the histamines have done their job, a really dilated blood vessel that can house loads of macrophage and allow them to slip through more easily to join the fight against this now replicating bacterial problem. If this battle goes poorly, meaning that the macrophage start to die in mass, a dying macrophage will release proteins that trigger your body to spike a fever. In order to increase your cell metabolism to allow the macrophage to grow and reproduce even faster, and to burn the invaders. So, bacterial cells, viruses, they are actually really only functional at a pretty small window. Our human body temperature is how most of them really prefer it. So if our temperature goes up 2 or 3 or 4 degrees, it actually becomes a really non-hospitable environment for bacteria. And that's one of the reasons we spike a fever. So there's a sad macrophage releasing those proteins. This is your brain. Your brain gets the message and says, we got to burn everything. And so it does. It absolutely spikes your temperature. This is why if you have a low-grade fever, 101, 102, you should not take something that reduces your fever, because you are actually slowing your body's response to killing whatever infection you have. Now, high fevers, 104, 105, 106, that starts to become really dangerous for you. Your body starts to overcompensate, and fevers that high can start to cause brain damage and really do a number on the rest of your system. But a fever of 101, 102, you shouldn't really take anti-inflammatories for, like ibuprofen or Tylenol, to try and knock out the fever, because the fever is actually doing you a favor. Those are the immune response notes for today. Yeah. Enjoy. Come by office hours if you have any questions.